Good morning, ladies and gentlemen. Today we're going to do episode 7, and I think I'm going to call it Circuit Elements, focusing on conductors and sources. So let's write that out. E 101, episode 7, circuit elements. We'll say conductors and sources. I've already kind of discussed conductors or ideal conductors in a few of my previous videos, so I think I'll just give a quick recap here on the main important points and then move on so I don't spend too much time belaboring that. So let me write this description. Well, first, okay, if I haven't already done this enough times, let me just put this here. And then let me write a description or definition of conductor, or an ideal conductor, at least in the case of our circuit. So a lot of the times when we say conductor, it's kind of implied that we're talking about an ideal conductor, even if it's not explicitly said. So let me be careful here. This is the definition. The definition I'm about to give is for an ideal conductor. So let me write this out. The voltage across an ideal conductor is 0 regardless of the current flowing through it. And all that means, like I talked about before, is I said in the general case, every circuit element will have if it has a voltage, that means there's a current flowing through it, and if there's a current flowing through it, there will be a voltage across it. And the catch, or the exception to that rule is the case of the ideal conductor, which carries current yet does not have a voltage across it. And no matter how much current flows through an ideal conductor, it will not have a voltage across it. And like I talked about in the previous videos with KCL and KCL, I kind of went off on a tangent about when we draw schematics and circuits and what these lines, what these wires mean. So in our circuit schematics, these wires that connect the circuit elements, which would be these rectangles, or an actual symbol, but right now I'm keeping it general. These lines are the ideal conductors. So we leave these out of our circuit analysis. They just represent the fact that these elements are connected. And these ideal conductors connecting our elements don't interfere with the performance of our circuit in any way. And you can see how that's the case. So if these ideal conductors, if these lines had voltage across them as current flowed through them, they'd disrupt the operation of our circuit, and then all of a sudden we'd have to model them with some circuit element. So we just say that these are ideal conductors and leave it at that, and we allow ourselves to draw our circuits this way. Now, and farther down the line, there may be times when you approximate certain things as ideal conductors, or there are some circuit elements under certain circumstances can behave like ideal conductors. But for now, you can just forget about that and just use this as a tool for your imagination and your schematic drawings that we use. Now I want to introduce a little bit more terminology before I leave this topic. If you've studied circuits at all, or if you've ever heard someone talk about circuits, you may or may not have heard the terms open and short. And you might know what those mean, but if you don't, I'm going to talk about them, because I think it can get kind of counterintuitive when you think about what these words mean. So let me draw two circuit elements here. And now let's say this end of each element goes off and does something else in the circuit, and we're just concerned with with these two elements right here, these two terminals of the two elements right here. Now, if I were to connect these two elements via an ideal conductor, this line right here, we would say these elements are shorted together. Okay, so when two elements are connected together via an ideal conductor or this line, we say they are shorted together. And in fact, another term for an ideal conductor is a short circuit. Before I drew this, before I connected them with that line, they were what's called open. So if no conductors or other circuit elements are connected between two terminals or two nodes in a circuit, if two nodes are unconnected by any path, any circuit elements or any conductors of any kind, we say that there's an open circuit between those nodes, and no current, exactly zero current, will flow through an open circuit, or rather an ideal open circuit. And so let me just write this here, and let me show this last example just so it's on paper. If I have two more elements here, these go off, do stuff. So these guys are open. Now I'm going to talk a little bit about sources. So let's write this here, sources. And there's really two types of sources you'll encounter in circuits. And if you might be able to guess based on the discussions that have taken place in these videos so far, the two types of sources are voltage and current. Voltage and current sources. And there is a difference between the two, although in a lot of cases it doesn't actually matter which you use, because currents will generate voltages and voltages will generate currents. But in many, many, many circuits, it really does make sense to use one or the other, or model some physical device as one or the other. And so there's an important distinction, and these sources have different properties that you need to remember. And so what I'm going to be introducing here are ideal voltage and ideal current sources, and those are mainly, they're really mathematical tools, and you'll find circuits that can come close to behaving like ideal sources, but when you get to doing real circuit analysis, you'll start approximating these ideal sources with models. So let's just jump right into this. Let me start by introducing the ideal voltage source. But before I do that, I actually have to make one more distinction. There's really another way we can categorize our sources, and that's by independent and dependent sources. And I think it's much more important for me to talk about independent sources, so I'll save dependent sources for either later in this video or another video entirely. I think it's much more simple to just introduce independent sources. So just keep that in mind. Right now I'm talking about independent sources. So let me, without further ado, ideal voltage source maintains a specified voltage across its terminals regardless of any connected circuit elements or its current. And before I talk more about that, let me go ahead and finally draw the first real circuit symbol that I'm going to introduce, and it's the ideal voltage source symbol. So there's even a few ways to draw this. Most circuit symbols have a few different stylistic options or methods that people draw it, but I'm going to go ahead and draw it this way. And so, like my general circuit element drawings, I have these lines, these ideal conductors that will branch off, and these little dots that I'm saying to indicate these are nodes. And the symbol here is this circle with a plus and a minus inside it. And that just indicates that this is a voltage source, and it indicates which terminal is positive and which is negative. And usually accompanying a source like this, you'll see some kind of subscript next to it that indicates the name of that voltage. So right here I'm going to write, to maintain generality, I'm going to write VS, V sub S, just for V source, voltage source. But depending on the schematic, whether or not this is a circuit that you need to analyze and solve, or if it's just a documenting schematic, this might just have a number next to it. This could say 12 volts next to it. So it could be anything. One thing to remember here is that this is totally general. So, I said here this is a specified voltage. Well, so VS could be a constant, it could be DC, or it could be a function of time. It could be AC or some transient. It could be more complicated than that. This is totally general. This could be essentially any function of time, whether that be a constant or something crazy. And a lot of times you'll actually see, in your analysis, you'll see voltage sources that are a function of frequency, which is also interesting. And I guess we'll talk more about that later down the line. Now let me talk a little bit more about this definition. So it says that the voltage across the source will be Vs regardless of what you attach to it. And so you can imagine if I have some general elements here, and these go off and do something, and I have an element here even, and this goes off and connects to something, but then these elements are connected to this source, or they're shorted to this source. We've closed our circuit here. So these are attached to the voltage source, and it does not matter what element A and element B are. And it does not matter what comes after element A and B. This could be absolutely anything. If this is an ideal voltage source, the voltage from this node to this node across the source will always be Vs, the specified voltage. And another part of this definition is Vs will remain the specified voltage regardless of the current that flows from the source. And so you could really say these two different specifications are the same thing. This is actually a little bit redundant, because it turns out that the current that flows out of the source is actually totally a function of what elements you attach to the source. So it's really like saying the same thing, saying whatever elements you attach will not affect the source. It's really because the definition of the ideal voltage source is that no matter the current that flows out of it, the voltage will remain the same. So no matter what you attach, and therefore no matter how much current is drawn out from this source, the voltage Vs will be the same, and that's the ideality here. So in real life, like, that's what makes this ideal. Every voltage source you ever work with will fail in this way. So you'll attach something, there'll be some limit, you'll start pulling current out of the source, and then it will no longer be able to maintain this voltage Vs. And so this, though, is a very powerful analysis tool early on, and this is, again, so this is essentially just a mathematical concept. Ideal voltage sources, like ideal conductors, are not real, but we'll use them all the time because it's very convenient. Now, to give a real-life example of a voltage source, and albeit not an ideal one, just a voltage source, I could just point to the battery, like I've talked about several times in my videos so far. Any battery ever that you've ever used in your car and your phone and a remote control, whatever, these are real-life voltage sources. So you have a 12-volt battery in your car, and that's exactly, it behaves like this, with the caveat that it cannot maintain its voltage, its advertised voltage, regardless of the current that flows through it. Any amount of current you draw from your battery will reduce its voltage by some amount. And ultimately, you can completely destroy your battery if you pull too much current from it. And of course, these ideal models that we use for voltage sources, in theory, we could pull infinite current from this source, right? But of course, there's no real voltage source that can behave that way. So a battery is a great example of a voltage source, and it's a familiar one that any person can relate to. So if you're really savvy, you may have noticed an apparent potential contradiction here with this definition of the voltage source. And so let me write this out. So if you've been paying attention so far, ask yourself what would happen in this situation. And what I've done here is I've drawn a voltage source whose two terminals are connected together via ideal conductors, or they're shorted together. And this is an interesting, this is an interesting contrived case, because essentially the two definitions of voltage source, ideal voltage source and ideal conductor, are conflicting here. So remember, the voltage across an ideal conductor is 0, regardless of any current that flows through it. And the voltage across an ideal voltage source is Vs, regardless of what's connected to it or the current that flows through it. So there should be a contradiction here. And well, there is and there isn't. In the plainest technical sense, yeah, there's a contradiction by virtue of the fact that this is just how we've defined these two things, but you can quickly put this paradox to bed by just remembering that neither of these things are real. There's no such thing as an ideal voltage source, and there's no such thing as an ideal conductor. And remember, the reason we use ideal conductors and the reason we use ideal sources is to help us in our modeling and analysis. So yeah, you will never encounter this ever, because this isn't a circuit that you'll ever analyze. This circuit isn't useful in any way. This doesn't represent a real circuit. Now, you'll have circuit elements in circuits that you analyze that approximate real things, and you'll connect them together with ideal conductors, and you'll drive them with ideal sources, and that all makes sense. But of course, yeah, you'll never encounter this situation. This doesn't make sense to model or analyze or even talk about. So don't worry about that. Okay, I think I've gone for kind of a long time on this video, mainly because I included a short discussion of conductors at the beginning, and I didn't expect going into this that I'd talk about this example case and this contradictory case. So I think what I'll do is I'll just end here and make a separate video where I talk about the ideal current source. And then I think potentially after that I'll make another video where I discuss the two quick cases of the dependent sources. So that's probably what's to come next. Anyways, thanks for watching. I hope this was helpful. If you have any questions, please comment or let me know what else you'd like to see in the future. And otherwise, have a great day.